In this video, I'm going to go over the examples from section 5.6, which deal with modeling with harmonic motion. Let's start with the first example. Find a model for simple harmonic motion that satisfies the following conditions. D of 0 is 0, the amplitude is 6 centimeters, and the period is 3 seconds. Now, simple harmonic motion is given by two equations, A cosine omega t equals d of t, or A sine omega t equals d of t. How do we figure out the correct equation? We use the first condition. So the first condition tells us that d of 0 equals 0. Let's see if that is satisfied by the first equation. So d of 0 equals A cosine omega times 0, that's 0. But we know that cosine 0 is 1, so the answer is A, which is not necessarily 0. So we know the first equation cannot be correct. Looking at the second equation, the sine equation, d of 0 is A sine omega times 0, which is 0. Now, sine 0 is 0, so the answer is 0, and the first condition is satisfied. So we know we're dealing with the equation for simple harmonic motion, d of t equals A sine omega t. Since the amplitude is 6, we know A is plus or minus 6, so we can simply choose A equals 6. And the period is 2 pi over omega, and that's 3. Solving for omega, we get that omega is 2 pi over 3. So the equation we're dealing with is d of t equals 6 sine 2 pi over 3 t. Another example with simple harmonic motion, we have d of t equals 6 cosine 3 pi over 4 t. First, we need the maximum displacement, which is simply the amplitude. So A, or the maximum displacement is simply A, which equals 6. Second, we need the frequency. We know that the frequency is omega over 2 pi. We know that omega is 3 pi over 4, so we know the frequency is then 3 pi over 4. Dividing by 2 pi is simply multiplying by the reciprocal of 2 pi. So the frequency is then 3 over 8 cycles per unit time. 3, we need the value of d at t equals 4. So we need d of 4, that's 6 cosine 3 pi over 4 times t, which is 4 in this case. That's 6 cosine 3 pi. But cosine 3 pi is negative 1, so the answer is negative 6. D of 4 is negative 6. 4, we want the least positive value of t for which d is 0. Now, if d of t is 0, this means we're looking at 6 cosine 3 pi over 4t equals 0. Well, 6 is obviously not 0, so cosine of 3 pi over 4t must equal 0. And the cosine is 0 at the odd multiples of pi over 2, so 3 pi over 4t must be a positive odd multiple of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, and so on. Notice I'm not taking the negative values because of pi over 2, 3 pi over 2, and so on, because that would give me negative time. And this doesn't make sense in the context of this problem. time must be positive. Now, the smallest positive value of t that gives me d equals 0 is simply the equation 3 pi over 4 t equals pi over 2. When we solve this equation, we get t is pi over 2 times 4 over 3 pi. That's 4 over 6, which simplifies to 2/3. Now let's look at damped harmonic motion. The first example is a stone is dropped in a calm lake, causing waves to form. The up and down motion of a point on the surface of the water is modeled by damped harmonic motion, which is given by the equations on the screen. At some time, the amplitude of the wave is measured, and 20 seconds later, it is found that the amplitude has dropped to 1/10 of this value. We would like the damping constant C. Now, when it comes to damped harmonic motion, the amplitude is dictated by Ke to the power minus Ct. So at time t, we know that the amplitude is Ke to the power minus Ct. 20 seconds later, so this would be time t plus 20, the amplitude is Ke minus Ct plus 20. What is the relationship they tell us in the problem? Well, they say that the amplitude at time t t plus 20 equals 1/10 the amplitude at time t. Notice how the k's cancel. Then E minus Ct times E minus 20C equals 1/10 E minus Ct. Again, E minus Ct cancels. So we're left with E to the power minus 20C equals 1/10. Applying ln on both sides gives us minus 20C equals ln 1/10. And solving for C gives minus 1/20 ln 1/10, which can be approximated with a calculator. Finally, we look at an example where a string on a violin is pulled at a distance of 0.5 centimeters above its rest position, then released and allowed to vibrate. The damping constant C for the string is 1.4. Suppose that the note produced is a pure G with frequency 200 Hertz. Find an equation that describes the motion of the point at which the string was plucked. Now, notice since the maximum displacement of the string happens at t equals 0, the damped harmonic motion must be a cosine function. So we must be dealing with d of t equals Ke minus Ct cosine omega t. Now, d of 0, so the string was pulled from resting position at t equals 0. Well, that's Ke to the power minus c times 0, that's 0. Cosine 0 is 1, and they tell us that this is equal to 0.5. So this means when you solve, k is 0.5. Furthermore, we know that the damping constant C is 1.4. We know K, we know C, it remains to figure out omega. We don't know omega, but we know that the frequency is omega over 2 pi, and that's equal to 200 hertz. Solving for omega, we get 2 pi times 200, that is 400 pi. So we're ready to write our equation. D of t equals k, which is 0.5, e minus 1.4 t cosine 400 pi t. That is the equation for damped harmonic motion that we are looking for.